Okay, folks, this lesson is going to be on bonding. So what is a chemical bond? Well, a chemical bond is when you have a mutual attraction between the nuclei. It's the valence electrons that are having the interaction between each other because they're the ones furthest away. And what ends up doing is that these different atoms actually bind together. And bonding, the reason why bonding occurs is because it needs to reach the minimum amount of potential energy. So all atoms are striving to do that. And when they're not bonded to something, they end up having very high potential energy. So therefore, they tend to combine and make compounds. Compound is when two or more atoms are bonded together.
A chemical bond is the force of attraction that holds two atoms together. As independent particles, atoms are at a relatively high potential energy. Most atoms are less stable existing by themselves than when they are combined. By bonding with each other, atoms decrease in potential energy, thereby creating more stable arrangements of matter.
So you can see that the whole reason why they bond is in order to decrease their potential energy, and this makes them more stable in nature. So there's two main types of bonding. We have ionic and we have covalent. So ionic bonding results from the attraction between a cation and an anion. So there's an actual positive and a negative part. Covalent bonding, on the other hand, is where they share electrons between two atoms. And we're going to talk more about this during this lesson because covalent bonding is what holds all of our molecules together for most of our substances in our body. So how do you really know if a bond is ionic or covalent? Well, in the textbook, they give you this big electronegativity difference. So when you have a bigger electronegativity difference, you're going to have an ionic bond. When you have a slight electronegativity difference, you're going to have a polar covalent bond. And when you have a huge or a very, very small electronegativity difference, you're going to have a nonpolar covalent. I'll make it real simple, folks. Ionic bonds contain a metal and a nonmetal, while polar covalent or nonpolar covalent bonds contain just simply two nonmetals. Again, let me repeat that. Ionic bonds contain a metal and a nonmetal, while a covalent bond will contain two nonmetals. That's the real easy way to determine whether a substance is ionically or covalently bonded. So let's talk more about covalent bonding, because as Barney would say, sharing is caring, but you know what I think about that. So let's watch a quick little video about the idea of sharing is caring.
Many atoms form covalent bonds. In covalent bonds, electrons are shared by both atoms. The first energy level in atoms can hold 2 electrons. By sharing electrons in a covalent bond, each hydrogen atom has a full outermost energy level. Water molecules are also held together with covalent bonds. Again, we see that covalent bonding gives each atom a full outermost energy level. The outermost energy level for hydrogen can hold 2 electrons. The outermost energy level for the oxygen can hold 8 electrons. In covalent bonds, the shared electrons move between the atoms that share them, forming a single electron cloud around both atoms.
So you can see that there's a merging of the electron cloud, and you notice that they started mentioning about the number of electrons around, and one of which I want to point out with oxygen, and it had 8. Interesting. So most living things contain molecules. A molecule is a neutral group of atoms that are held together by covalent bonds. Okay, so just about everything in your body is held together by covalent bonds. And they have specific formulas based upon the idea of the law of definite proportions and the law of multiple proportions. And so molecular formulas give a ratio of each compound. So you can see some examples there of H2O, meaning there's 2 hydrogen for every 1 oxygen. C6H12O6, that's glucose, 6 carbons, 12 hydrogen, 6 oxygen, and then you have our famous O2, which is oxygen. Okay? And so those are all the formulas, and we're going to show ways in which to bond these. So the formation of a covalent bond is kind of unique because what ends up happening is there's an attraction of the nuclei and electrons. But remember, there's also repulsion between the protons and the electrons. So therefore, there's this distance that ends up occurring between the atoms when they are bonded, and they actually end up overlapping their electron clouds. And this overlapping portion of it is where the bond forms, and that's where electrons would be shared. They're sharing in order to reduce their potential energy. Now, this attraction and repulsion will actually determine the length of the bond. So the way it works is the shorter the bond, and this comes down to also the size of the atom, the smaller the atom. So the shorter the bond, the stronger the bond. The longer the bond, the weaker the bond. And that plays a big key role when we start talking about substances that are more reactive than others. And when atoms bond, their potential energy decreases. And this potential energy that is now, again, potential is the idea of stored energy, is stored actually in the bond. That's why when we consume glucose, when we break the bonds, we get the energy from it. That's the energy that was stored from the formation of the glucose. So, and again, these covalent bonds, there's an overlapping the orbitals, and that's where the electrons are shared. Now remember, these electrons are constantly moving, so they're not always shared equally, and we'll talk more about that later on.
Chemical bonds form when reacting atoms reach a lower potential energy when bonded than those same atoms would have as independent particles. In forming a covalent bond, electrons are shared and energy is released. The same amount of energy is needed to break them apart. This is called the bond energy. Bond energy varies with different kinds of atoms, as shown in this table.
So you can look and see here at these bond energies, and what it really is trying to show us is the length and the size of the bond. So the longer the bond, the less energy it takes to break it apart, because the nuclei and the electrons are so far apart. And the big thing is the nuclei difference. And then you've got other bonds that are very, very strong, such as the hydrogen-fluorine bond, the HF at the very top with 570, and that's because those molecules are those atoms are very, very small. So how many bonds does an atom really want to make? Well, it all depends upon how many valence electrons it has. Remember, the magic number and what all atoms are trying to achieve is 8 valence electrons, okay? 8 valence electrons. And the reason it's 8 is because of the noble gases. They are the most stable atoms on the Earth. And therefore, this leads to what's called the octet rule, meaning that every atom is trying to achieve 8 valence electrons. Now, of course, there's exceptions to the rule when it comes to the octet. Some atoms actually can exist with less, some actually can exist with more, and then some don't follow the rule at all. And we'll go over those as time progresses through this unit.
The noble gas atoms are the only ones that exist readily in an isolated state in nature. The outer s and p orbitals of these elements are completely filled with electrons. 8 in most cases, and 2 in the case of helium. As a result, these atoms have low potential energies and stable electron configurations. Other main group atoms can effectively fill their outermost s and p orbitals with electrons by sharing electrons through covalent bonding. In this way, each atom has a stable noble gas type structure. Let's look at this same combination of atoms using orbital notation. If we join the unfilled orbitals of 2 atoms with a box, we see that the combination fills the orbital. There are, however, some exceptions to the octet rule. The most important ones relate to the elements hydrogen and boron. Hydrogen forms compounds to share a pair of electrons, filling its s orbital. Boron has only 3 valence electrons, and so forms compounds to share 6 electrons, filling its s and 2p orbitals.
So you can see that there's exceptions to the rule, and they're just showing the idea of these 8 valence electrons. The key number to remember is 8 valence electrons.